Hello everyone, welcome to today's webinar. I'm Karen from EngineSoft and we're excited to be introducing the hydraulic solution Fluidit today. In this webinar, we'll be looking at how it is used to tackle CSO spill impact on the environment. Today, we're joined by my colleague Bipin from EngineSoft and Hannes from Fluidit. Would you both like to introduce yourself?
Thank you, Karen. So I'm Bipin Patel, co-founder and MD of EngineSoft UK. My background is engineering, but got interested in the water sector about 2008, looking at how we could deploy algorithms and AI in solution optimization. Over to Hannes.
Hello everyone, I am Hannes from Fluidit. I am a water engineer with 15 years of experience in urban hydrology and hydraulic modeling both in Finland and in Australia. At Fluidit I work as lead engineer spearheading the development of the Fluidit simulation software tools for sewer, stormwater and flood modeling applications. I am pleased to share more with you later, but for now, back to Karen.
Thank you both. So before we get started, I'd just like to remind everybody that you have just been muted for the efficiency of today's webinar, but feel free to use the chat box to ask any questions that you might have throughout. We'll endeavour to cover as many as we can at the end of today's Q&A section. But let's get started. Back to you, Bipin.
So before we go into the case study, let's talk about the journey so far, just to set the context and why we're here where we are today, talking and partnering with Fluidit. So our journey started many years ago, and as most journeys in the UK, we've had our bumps in the road, and sometimes we've wanted to turn back, sometimes we've wanted to crash through the challenges, but we've had to work through them and get to the point where we've got to. So it started off where we tried to connect an optimization platform to InfoWorks CS and realized that it wasn't possible. So we had to write some custom software, we referred to as an interface at the time, and got the two software talking together. And that was a very important stage because that meant other things could now be achieved, such as optimization. So we started working on projects for smart optioneering, and then later on verification projects. And they allowed some efficiency gains and some kind of capital savings, sorry, not capital gains, capital savings for optioneering projects. That API now is a full-blown software that we're developing, and that's development's ongoing. It has carbon capture, it has cost models, it has verification, target setting capability. So it's got full functionality, and it allows you to connect optimization software to hydraulic modeling. So a very exciting development, which now is much more accepted as it was compared to, say, in 2010 when we first started working. Then a few years ago, we started again responding to the demands of our clients and developed a growth impact demonstrator, which has now matured into a fully fledged platform called Strategic Giant, which stands for Growth Impact Assessment tool. And so essentially allows a non-modeler, say a growth manager, to conduct a single point hydraulic simulation, understanding the impact of population growth, climate change, etc., etc. So, and the purpose of that is to alleviate the demand on the modelling team, which is just obviously just increasing at a pace, and it allows the development team to have a little bit more kind of responsiveness to their questions that they're asking. Moving on from that, and by the way, I should say part of that Strategic Giant platform now is a very interesting functionality called interactive reporting. So once you've generated your numerous designs from optimization, you have a data mining tool, essentially, and a decision-making tool within Strategic Giant to be able to analyze those results to help decision makers and stakeholders come to an efficient decision. Over the last 2-3 years, what we've been working on, some of you may have seen Sam Trent's presentation at UDG at SciWim last November. We've been working to look at how we can deploy all of these techniques and capabilities in DWMP, modelling and understanding of the impact of various scenarios over time horizon, and that's also led to kind of development of techniques and software for SUDS sensitivities and SUD prioritization, and also more recently spill reduction. So some very exciting developments really to shout about. Where, these issues are very prevalent and very current for all of you on the webinar, and we're very pleased to say that we can offer some assistance in that area. So Fluidit, how did we start? How did we end up here with Fluidit? So a couple of years ago, maybe 18 months ago, we started thinking, okay, we'd like to be in a position where we have some control over what some buying power, let's say, rather than just being dependent on one tool. So we wanted to look for a good kind of second option or an alternative in certain situations to ICM. And we came across Fluidit. We've been working with them for a year and a half, and that's culminated in a partnership. And it's we're very excited about it, and you're going to find out more, obviously, on this webinar about that hydraulic modelling platform. So I'm not going to say a huge amount more about that for now, but we can come back on it later. I'd just like to cover where we feel our expertise lies and what qualifies us perhaps to assess new software for the industry. So we have 35 years experience in 1D, 2D and 3D simulation. We've been working in that field, and we are experts, I would say, in engineering simulation. So that, I would say, in hydraulic modelling for the last 13-14 years we've been working with, specifically in the water sector, and not just hydraulic modelling generally. And over the last few years we've been deploying our expertise in automation, process automation, in design optimization or solution optimization, and data science. So that has led and culminated into our ability to develop our own software, such as Strategic Giant or the API or interactive reporting, which we can now make available to, obviously, anybody that's interested. And we feel it qualifies us to assess sensibly the tools and alternatives that are out there that can benefit the industry. So I wanted to share some of the kind of assessment or the findings that we have kind of uncovered by talking and listening to our clients. We see that there's a huge increase in workload over the last few years for the demands to the industry. The simulations are potentially getting slower, and especially if we're looking at 2D, then that's quite unmanageable, we would say, in the current software portfolio. And there's limited modelling resource, right? So and that's where we felt tools such as Strategic Giant could assist in cutting down the workload for the modelling team, for instance. There's a huge need for automation and AI, and we've been working with our clients to help automate various processes. And there's issues, obviously, with license sharing and license costs, especially with the new models that are being proposed. So we feel them, because we're obviously users, and you probably maybe are experiencing some of the similar challenges that many of our clients are facing. So as a result of the challenges that we're all facing, Enginsoft have decided to partner up with Fluidit and distribute their software in the UK. So we're very excited about that development. We feel it's a great product and a fantastic team, a technical team behind it to support us all in being able to meet our future challenges. So over the past year, Enginsoft and Fluidit have been working together to understand the commonalities and differences between Fluidit and ICM. And in doing so, we realised very quickly that we needed to, the first task was to convert existing ICM models into Fluidit. So we've been working on a product that allows that to happen. It's not fully developed yet, but probably useful in the sense that we can convert a large proportion of the ICM model into Fluidit in a kind of automated fashion, which is quite exciting, and we've been using it. So suffice to say, the converter is a work in progress, but we have got some initial results to show the difference between the two software. And as you can see, the lines are pretty much on top of each other, so we're reasonably confident that we can obtain similar results in both products, which is exciting. And it's within a reasonable kind of degree of expected difference. You wouldn't expect two different software to produce exactly the same result. But we do feel that the difference is likely to be less than what you would typically expect between simulation and observed data, or if you run on two different PCs, you might get a different CPU, and that might give you a different output in any case. So as you can see, the kind of the volume and the flow results for two kind of flow monitors that we've got here are very, very similar. So we've carried out some benchmarks, and it's not a finished product. It's certainly a work in progress. There are some parameters that don't transfer over directly and need further investigation. So it's an ongoing piece of work, but we're quite satisfied, I would say, and encouraged with the results that we've got today, enough to obviously announce this partnership. So there's no real effectual difference in the simulation runtime. The results are less than 5%. Tests show that kind of Fluidit is quicker using the same time step, but it does require a smaller time step due to different methodology. So in other words, there's not a huge difference in certainly the 1D. I think Hannes will be talking about 2D, and I think there could be some real advantages in their approach to 2D modelling. But we've got, if you'd like to dig a little bit more into detail about the benchmarks and the conversion process that we've talked to, obviously we'll be arranging any meetings that anybody requires after to go through in detail those findings. I'm sure lots of you have got questions or down to ask, but feel free to drop them into the box, and then we can deal with them later, or on a one-to-one basis if it's a more detailed discussion. But let me hand you over to Hannes from Fluidit, who will talk us through the software and the solution, and via a case study. They've been working with Helsinki Water Board for many years, and there's a very, very interesting case study that obviously he's going to take us through. So over to you, Hannes.
Thank you, Bipin. To set the scene, I will first give you a brief introduction to the Fluidit Storm solution that was adopted for this case study, and then we will move on to the background and implementation of the project. So let's start. So to begin with, Fluidit Storm is an integrated catchment modeling software solution. So as you would understand, it has the catchment hydrology module, network hydraulics module, and then the flight analysis module that are all put together into one solution. In addition, it's important to note that there's plenty of options and opportunities for data management built into the software directly. So you can play with digital elevation models, network data, GIS data. You can edit data in bulk, and also you can customize and program with Python to do further advanced models. Then also, as in this case study, you will also learn the version control is very important. So there's an opportunity for multiple people to work on the same model, and then also have a 100% proof track record of changes and versions. And then importantly, again, in this case study, you learn that the data connections have been vital. So you can connect all kinds of SCADA information or weather information directly into the software without further third-party components or anything, directly in the software. And then how you obviously can use this software. Today you'll see one example, but more broadly speaking, it could be this CSO discharge analysis and quality simulations, but there also could be stormwater management, planning and design work, or it could be catchment-wide green infrastructure studies. It could be also the sewer system optimization or various kinds of flood mitigation projects. And lastly, I like to highlight that, as modelers, as designers, we always do work in multiple levels. So sometimes it's very important to be able to do some simple and quick analysis. And that's where we provide some really fantastic tools to build a model quickly, run some simulations, and then visualize and analyze everything rapidly in the software itself. But today we go more to the deep end, and an example about comprehensive data analytics, some customized work, and so on. And here we are. Today we talk about Case Helsinki, which eventually was a CSO real-time project, but it has started as a bit more typical modeling project years ago. But we'll soon see how the story goes. So this project is prepared for the Helsinki Region Environmental Services Authority, which is the largest water utility in Finland and operates on the Helsinki capital region. And this particular project where we developed this real-time model was heavily supported by the Ministry of the Environment through their water protection program. So big thanks to all these parties. So let's see what's been the motivation and the background for this project. So when we started a few years ago, there was a really strong will to understand the overflows in the network. To start with, Helsinki obviously is a quite old city with old infrastructure and some pipelines almost not properly known, as you can understand. So the problem was, can we really monitor somehow and mitigate overflows at city scales? Not only at some pumping stations, but anywhere in the network in the city. And to put this into perspective, HSY is a rather large player here in Finland. So they operate the two largest wastewater treatment plants over here. And also where this case study is focusing on is the Viikinmäki wastewater treatment plant that services around 860,000 people in the Helsinki area. And here we have some annual rough numbers of the overflows, so 84,000 cubic meters a year roughly, and 13% of that is on average sewage, and then a lot of stormwater, of course. So why they are modeling? What is the purpose? So I've to highlight a few points here. So to start with, HSY reports the total CSOs based on modeling at 3-month intervals. And why is this? It's because there are no direct overflow measurements in the network, and there are several reasons: the cost, but more so the traffic hazards and hard installation and maintenance. Often these overflow locations are in the old part of the city, in heavy traffic areas where it would be very dangerous and also complicated to install any of actual measurement devices. So that's why they use a simulation software to then simulate and estimate the overflows. Well, the other side is that with the model, they can get an overview of the combined sewer system performance anywhere in the system, regardless of the part of the model. And with that, they can of course go more towards planning, as they do, so they can plan options, plan scenarios for CSO mitigation. And then, as today we will learn more, that they wanted to go towards developing a real-time CSO monitoring and alarm system. And that's where we are heading in this case study. Okay, so why would you need a real-time model? What's the point? Well, let's imagine that there has been a heavy storm in your city. Would you like to know about the severity of the CSOs within 1 hour? Or are you happy with knowing after 3 months? And this has been the case in Helsinki, as they only sort of reported and properly observed the CSOs after 3 months as part of the quarterly simulations. So obviously that is a long period to wait, and you cannot even react properly to the CSO events. So therefore, they've been driving towards this real-time application, and obviously it has been a challenge for the citywide model, but in this case study we've done that. So now they can react within, let's say, 1 hour. But let's step back a few steps and see where they've been coming from. So HSY has a rather long history with network models. So started modeling already in the mid-90s. We fast forward to 2012. That was the last calibration of the old model they had. And then eventually they started a major update project in SWIM in particular. At that point, they decided also that, okay, we should review the network information. We should sort of fill in the gaps of missing information and review that everything is correct. And that's quite a job for the 3,000 kilometer network. Also, in that same moment when they started the upgrade project, they tried the EPA SWIM approach as a free software and so on. But it turned out quite quickly that with this scale of a model, the whole city network, it didn't provide a suitable performance for this kind of application. And then they started looking for alternatives, and since SWIM models can be imported directly to Fluidit software, it was quite straightforward to check how this could work. So before too long, we started working with HSY developing the new CSO model in Fluidit Storm in 2020. Then finally 2021, this new model was adopted for CSO reporting and has been used for the reporting ever since. And then obviously that wasn't yet enough, so they were really wanting to push towards the real-time model, and therefore in 2022 we ran the pilot project to develop the real-time model of the whole model, and here we are today showing you some of the conclusions from that work. Okay, so now we talk about the model. So what is the model? Let's have a look at some technicalities, what that includes. So briefly, here we have a bit of a broad map of the model. So we have a combined sewer area of 17 square kilometers and a separate sewer area roughly 24 square kilometers, plus there are quite substantial flows coming from the regional sewage networks, all the way to Viikinmäki wastewater treatment plant. So in this model, we have about 480 kilometers of network and 220 of which is combined sewer. And it's a detailed model. That's the main point, that we haven't done like a skeleton model. It's a fully detailed model with all details included. Ultimately, there are 50 overflow locations and 26 pumping stations of various sizes. In terms of the hydrology, this model is interesting. So we have used a specially varying radar rainfall at 5-minute intervals. So we've derived from the radar rainfall 250 locations distributed on the model, and they will provide quite local rainfall estimate for the catchments. Then on the catchments, as we are in a swim-based model, there's a very thorough rainfall to runoff processes simulated. Also importantly, for the springtime, we simulate the snow melt processes. So because the spring flows can be up to threefold compared to a typical flow rate. So the snow melt estimation is very important part of the spring overflows. Then on the catchments, we also simulate the soil parameters, and we are using detailed land cover data to estimate all the catchment parameters. In terms of the flows, we have the groundwater infiltration, of course. Then we got the base wastewater flows based on patterns and typical usage. And then there is the storm peak, which could be caused by the rainfall or the snow melt. And also in the model, we can separate what part of that water is actually sewage and what part is stormwater. So if you imagine that you could tag water, we can see the tags and see how they accumulate and where are we actually discharging more of sewage and where we are discharging more of stormwater. And we've included these 5 indicators or pollutants shown on the screen that to get the pollutant loads calculated as per the environmental permit. Okay, so this is the broad picture of the model on a plan. So what about the real-time process? What does that mean actually? So what is going on at HSY is that they have a model on their server, safely on their server. There are direct data connections to external sources like the SCADA and weather data, and then the model is simulated on the server, and then it will output results to another system. So if we look at this this figure on the screen, we can just simplify this whole topic a little bit. So this is how the real-time model typically works. So on the left, we got the input data part. So we have 2 different interfaces to obtain the climate and weather data, and then we got the SCADA data and precipitation coming from another interface. All this is imported to the model using automated processes. Then in the actual model, it will simulate itself based on the settings we've provided. It will pre-process the inputs first, then simulate, and then post-process the results. And then it's time for export. Now it will export again as instructed to different places in the system and also in specific formats. And once that is done, then let's repeat. And then the whole cycle will start again. And now it's set up to repeat at every 1 hour. So furthermore, so what is this near real time? Are we actually in real time, or is this sort of near real time? Well, we can call it near real time to be true. So it is at this point a hindcast simulation at 1 hour interval. So we are within that 1 hour, time window that we are modeling the past hour. And the reason for that 1 hour limit at this point has been that the pumping station flow data could only be obtained at 1 hour intervals. But then with a lot of discussion, is there potential to increase the simulation frequency? Yes, certainly there is. The other data sources are much more frequently updated already. For example, the precipitation is received at 5-minute intervals, and only the simulation of that 1 hour of the whole network only takes about 2 minutes. And then the data processing after that is also very rapid. So basically you could shorten the interval to much shorter time if the pumping station data would be a bit more frequent. But there's always some bottlenecks in the process, but we are working through to get all the data updated more frequently in the future. Okay, so what do we get from these simulations? Of course, importantly, where do the overflows occur and how do they look in time? So you get hydrographs and the flow graphs and pollutant loads from various locations on the network. Typically, we report the quantity discharged, so cubic meters, pollutant loads in kilograms, and then also an important and interesting factor is the share of sanitary sewage. As I mentioned earlier, you can identify anywhere in the network how much sanitary sewage the network is conveying, as opposed to stormwater loads. And then, importantly, now we got real-time results. So any CSOs are known within minutes. So now HSY can react, they can take action, they can warn. And as I said before, it was 3-month gap between the actual overflow and the proper data about it. And that was too late for meaningful action. Okay, so these are the main types of results. Well, how the results are often used is, again, another thing. So we provide many highly visual results to HSY. They could be, for example, these kind of dashboards where we collate some key information of from the overflow locations, like on this graph in the middle, the overflow card. There we can see, for example, we can always refer the overflows to the precipitation to make sure they are making sense. You can calculate accumulated pollutant loads, and also you can see a time series of the pollutant loads. So when did the actual load happen and what was the magnitude of that? You could also analyze the pumping stations, the efficiencies and emissions and so on, and then have all kind of data, whatever you need to operate your system well. You can have them collated on these dashboards that are easy to share, and you can have a bit quicker view of your operational status. But the current state of the real-time model, HSY has an external system. They already had it for many years, and they output some key results to that system, and then they sort of take the data and use it as they see best in the existing data platform. Another aspect I like to highlight that what HSY can do is that they can actually analyze the overflows as a 1D, 2D model. That helps them to communicate where do the network overflows happen. So for example, if I show this short animation here, so it's a typical case where the rainfall loads the 1D network, and then let's stop here. So we start seeing red on the map, of course, and as the overflows occur on the network, it will be turned into a 2D flow on the surface. And then you can properly analyze where are the overflows going, for how long they stay on the surface, and therefore you can make better strategies for reducing overflow and risk. Also assess the hazards for the infrastructure and people. So if I continue the animation, you can see that the water is flowing on the surface, and then is much more useful result for overflow analysis than only seeing, let's say, red dots on the map. And this is very easy to implement if you have a 1D model already. it's a couple of extra steps to then add this 2D analysis of the overflows. So this is something HSY is also exploring for their planning purposes. Okay, so the results. To start with, the real-time pilot was a successful project. That's the main thing. It wasn't sure if it can be done at city scale at this detailed level, but it certainly could be done, and it was successful. The key benefits were identified, and that was important for the utility to really understand and see, okay, what can we get out of this kind of model? Well, importantly, there's a prompt action they can take for the CSO incidents. So let's say they can now react within 1 hour. And also, importantly, the reporting steps are much easier now that they don't anymore have to do the 3-month CSO simulation, which was quite tedious process, lot to simulate in one go. Now they can only focus on the past 1 hour. And that importantly, that allows them to make the model in higher detail. So can you imagine that now you can have a much shorter time step compared to that of the 3-month simulation. So now you can simulate basically time step of, let's say minutes or even seconds. And then in the 3-month case, you would be using some, longer 5 to 10 minute intervals, for example. So now we can achieve much more accurate results and better response for the stormwater incidents, especially for the highly varying rainfall events. And with the same technique and the same system we have now already built, this can be further developed into a forecast and warning system. And this is certainly the goal, as you will see soon. And as we get a quick response to the CSOs, now HSY can also plan some sampling. If they see that, okay, now there has been a CSO just 1 hour ago, okay, let's go and put a sampling device there. So there should be another rainfall coming in the afternoon. Let's go and get some samples out of it. And importantly, as it has been an automated process, it does increase the consistency of the modeling significantly, I'd like to think. But as with any automation, you need very good processes to verify your data and see that everything is working as you think they are. So that's been a big learning as well, and to develop these the processes to make sure everything is working well within the automation. Okay, so as to wrap up, just briefly some next steps that they are planning in Helsinki. At least that's good to have the long horizon to plan for. So currently, the real-time pilot is what has been completed, and we are just moving to the real-time in operation. So the actual model will be then used for the operational purposes, and it will replace the traditional 3-month simulations. The next goal would be the forecast and warning system pilot, and obviously from there they would like to move on to have the forecasting features in operation, and then once that is proven, then the warning systems in operation, and then it would be very interesting to have the 1D to the flood risk forecast within this model too, and it is certainly possible with the same technique. And eventually there could be a holistic urban water forecast system that would take into account the CSOs, the separate sewer system, stormwater and flooding, and that's the big picture for the utility. Okay, but it's time to wrap up. Thank you very much. I'm happy to answer your questions later in this webinar. Thank you.
Well, thank you very much, Hannes, for that very interesting case study. And I can see that we've already had some questions, so we'll get onto them in a minute. But let me just finish off by talking about what might be the next steps for everyone here. So we've got obviously a number of technologies, a number of initiatives that we're working on, including Fluidit, and we'll be doing further webinars webinars on some of these topics, but if in the meantime you'd like to discuss any of them, feel free to get in touch. So we have a very exciting democratization tool, and if you're struggling with the growth development kind of impact work, then it's worthwhile having a look at that. We think, especially with Fluidit now, the digital twin possibilities are becoming closer in terms of real time and in terms of managing that data, managing the simulation runtime, and obviously 1D, 2D optimization certainly becomes possible with the kind of the version of 2D that Fluidit offer, the uncoupled version. So we'd be very interested in talking to anybody who's interested in exploring that further. Obviously, we have the obvious sensitivity, interactive reporting, the DWMP type of work that we've already been discussing. That's also available. But let me finish off there and hand over to Karen, and we can do some Q&A.
Thank you, Bipin, and thank you very much, Hannes, for helping us understand how Fluidit can be used to monitor the CSO effect on the environment. Okay, everyone, so before we end, we're just going to move into Q&A, a chance for you to ask any questions that you might have on any of the aspects that we've covered today. If you do have a question, please feel free to use the side panel that appears on your screen, and we'll get to as many as we can today. So let's move on to the first question. So this first one's for you, Hannes. If I'd like to develop my current network model into a real-time model, what would be the main considerations?
Okay, so thank you for your question. So if you'd like to start developing a real-time model from your current model, first you should always check and sort of review that you have a good enough network model overall. That is your data of suitable quality and suitable extent. As the real-time technique itself is a matter of automation, so it can be made work, but it is more meaningful if you have a good enough model and good enough data connections. So for example, do you have measurement data available from the key locations in the network? Is it good enough for calibration and also to validate the model? And also then you should be testing, planning the test processes for data checks. So how do you get a warning if something is wrong in the data flow? But the real-time models are always built on a case-by-case basis. So it's important to have all these technical discussions early. And also you could immediately start removing any potential bottlenecks from the data flow and start working towards a good system.
Thank you. A few people have asked about today's webinar slides. A copy of the actual webinar recording will be sent out following today's webinar in an email. But if you do have other colleagues that you'd like me to share this with, please feel free to email me those details and I'll get that passed along to them as well. So the next question for you, Hannes, is a real-time model more accurate than a typical network model?
Okay, thank you. That is a question I hear a lot actually. So is the real-time model more accurate than your normal model? So in principle, no. It's the same model as you would have anyway. So that's not the point. But the difference is that like in this case study I said that the real-time model is only focusing on the past 1 hour. If we compare that with the typical solution in this case, that it was simulating 3 months. So that means it's over 2,100 hours. So meaning that it had to be somewhat simplified in terms of simulation parameters and so on. While now, as we are only modeling 1 hour, we can make it very, very accurate in terms of the time steps and other settings. So obviously in this particular case, as we can now shift to more detailed simulation, the model is more accurate. And I believe this would be the case in many many other places as well that you can then start focusing on the finer detail as you can reduce the time of the simulation.
Thank you for that. And can flood simulations be added to the real-time simulation cycle?
Okay, thank you. So the flood simulations can be added to the real-time cycle. The only limiting factor would be the simulation time needed to complete those 2D calculations. So in this case, as we are in the Fluidit Storm software, it is possible to use this really fast flood simulation method for network overflows. So in this case, the 1 hour cycle would be enough for quite a large part of the city. But if we were to simulate the whole city in 1D, 2D, we would very likely need to then extend the cycle, something longer. Let's say 2 or 3 hours to have enough time to simulate the 2D and also post-process the results. But basically, it would be just like adding one step into the process. But so technically speaking, no challenges, but it's more so the time factor. But in this case, I would recommend using the flood simulation only for some particular areas that need your attention. For example, some key locations where heavy overflows or high overflows are likely. So you could easily have a model where the 1D simulation covers the whole city, while the 1D, 2D focuses only on some specific areas. And this way you could optimize the use of time and also the production of results and data in the process. So that's what I would recommend.
Okay, so unfortunately that's all we've got time for today. I'm sorry if we didn't get a chance to cover your question, but either myself or my colleague will be back in touch with you after today's webinar. I hope you have found today useful and informative. This will be a part of a series of webinars, so if reducing CSO is important to you, keep an eye out on our social channels and our emails. Just before we go, I'd like to thank Pippin and Hannes again.
Well, thank you, Hannes, and thank you, Karen, for arranging this webinar and for Hannes to present. It's been excellent. Thank you, everyone, for attending, and we hope to touch base soon. Thank you. Bye.
Thank you, everyone.
That's it, everybody. Hope to see you on the next webinar. Thank you.